Can you see my screen? Can you still see my screen?
No, you need to turn it back on again.
Okay, so I will share this one more time. Okay, so we will go back again to slides, and we will go to principal component analysis, I guess. Yes. I mean, today, I mean, Magnus, he will be working on this, and also if other people try to make it, just to share with me, in fact, after finishing this BCA. I mean, BCA, we have been discussing BCA before. You can just imagine that principal component analysis, it's an algorithm which takes all features as an input, and it will produce a new feature, new set of features of the same size, but it will be, we call it principal component. It will be in different coordinates. In fact, those principal components, it's the eigenvectors and eigenvalues. Each eigenvector has an eigenvalue associated with it. I mean, and this eigenvalue will represent how much variance, how much knowledge it carries from the data, from our data set. So it's similar to k-best, for example. I mean, in select k-best, we provide it with a set of features, and we will get a score, right? And you can just select, I mean, the index of the top 5 or the top 10 best features. But the idea here in select k-best, the input, I mean, the output features, it's just selecting the most powerful features from the input set. It does not transform it to any other form. In fact, it keep it as it is. So if it is a pixel value, it will stay as a pixel value. And when we reconstruct, in fact, we just need to reshape it and just display it to see if it still has any value, any meaning of from the input features, for example. So we will test it with Magnus. But in case of BCA, the input will be just features, and the output will be principal components. Those principal components, it's eigenvectors, and associated with it eigenvalues. When eigenvalues it's high, it means this eigenvector carry lots of information from my data set. But those principal components, they does not have any physical meaning. So for example, if we have a data set, and this data set is about banking system, so one feature is age, one feature is income, the other feature, for example, it's education, for example. If he will use principal component, the input will be 3 features and the output will be 3 features, but the output features does not have any physical meaning. You cannot say that, okay, this one should be the age, this one should be the income, this one should be the gender or educations or whatever. No, principal components does not have any physical meaning. It does not have any meaning for my problem. They are just eigenvectors, and each eigenvector has an eigenvalue associated with it, and we can sort them in descending order using those eigenvalues. And you can just select the principal component which has the highest. You can select the first, I mean, 2 principal components which has the highest eigenvalues, and so on. So in fact, we provide it with inputs, we get some outputs. So the outputs will be principal components. Those principal components, it's just eigenvector. We sort them in descending order, and we can pick some of those principal components. Those principal components will be very powerful for training my model, right? So for example, in MNIST dataset, we have 874 or 784 pixel values or features. We can send them to the principal component analysis, and we will get the same number of features, by the way. So the number of outputs will be as the same as the number of inputs. Each eigenvector will have an associated with it eigenvalue. We can sort them according in descending order, those eigenvalues, and get the index of the most powerful. It will be sorted anyway. So you can select the first 10, the first 100, the first 144, and you can use those, and you can reverse transform to reconstruct the image, for example, and you can see how much information still we have from those 144 principal components, for example. So in this example here, we have principal component. So for example, I can just give you an example. You have a data set like this one. You have, I used it last year, in fact, in my slides, but I mean, I have a problem each year. I just make new slides. So you have a data set like this one. right? It's in two-dimensional space. It's like this one. So in fact, in the principal component, this one, it's x1 and x2. Maybe x1, it's age, maybe x2, or years of experience, and x2, it's the income. Similar to the regression model, which we did maybe in the first week or second week. So principal component will be this one. This one will be the principal component. In fact, it's the vector which has the list of variations. This one will be the principal component, and perpendicular to it will be the second principal component. So now we have two. I will call it x1 dash and x2 dash. So in fact, if I need to plot x1 and y dash and x2 dash, it will be like this one. It will be something very more beautiful, in fact. So it will be x1 dash, x2 dash, and data will be centered here. In fact, this one will be, sorry, this one will be in the middle here. So data will be centered, more organized, more beautiful. So it will be much. So this x1, it will be more powerful, in fact, and the x2, which is perpendicular to x1, it will be also more powerful than x2. So now I transformed the data from this original domain into a new domain, in fact, a new coordinate system, from the original coordinate system into a new coordinate system where the data are more distributed. I mean, it's distributed in a much better way, and the data can be explained more in the direction of x1 and x2. Each x1 and x2 has some eigenvalues. So maybe the eigenvalue here will be 0.8. Maybe the eigenvalue here will be 0.2, for example. This 0.2 and 0.8, for example, it will describe how much variations in that direction, how much the data, how much variation in direction of x1 dash and x2 dash. But if x1 was, for example, years of experience, and x2 was maybe something else, education, for example, now x1 dash and x2 dash does not have any meaning. In fact, does not have any physical meaning. It's like some geometry, for example. It's something coming from geometry. We try to find the principal component or the direction where data has more variations. Now we will use BCA. We will apply it to iris dataset, I guess. No, in MNIST dataset. So first we have, and the BCA, it's unsupervised technique, right? Why it's unsupervised? Because we are working with features, correct? We are not working with target. We are not working with labels. So my MNIST dataset, it's about images. So each image and each image has a label, for example, 0, 1, 2, 3, 4 until 9. No, we are not working with the labels. We are working with the features, only features. So it's unsupervised learning approach or unsupervised algorithm, and it is used to simplify the data and to reduce and compress the data. In fact, it reduces it because if I have an MNIST data set, I have 784 features, right? I can represent the image. In fact, I can reduce it into 144, for example. So instead of using 784 features, I can just use 144 features. And in this case, we call it dimensionality reduction. Dimensionality reduction. We reduce the dimension of my feature so we can simplify the model. So if you want to use a classifier, instead of building a classifier for 784 inputs, I can build a classifier for 144 inputs, right? So now the model should be simple, because you can just calculate number of parameters, and then when we use 144, the number of parameters will decrease a lot. Because if you have a hidden layer, and if this hidden layer has 100 nodes, instead of multiplying 100 by 144 or by 100 by 784, it will be 144. So it will reduce. In fact, it will reduce the model capacity, and then when we reduce the model capacity, it will take less time for training. It will require less amount of data for training it, and the chances to overfit will be much lower, right? So it will be really much better when we use BCA, for example, or any other techniques. There are lots of techniques. If you want to use BCA, you can just import it from sklearn.decomposition. We have BCA. We have the MNIST dataset. I got it from sklearn here now. We have been just discussing with Magnus how can we get MNIST. We can get MNIST from Keras or from sklearn datasets. So now I have it. I didn't divide it into training and testing because I'm not training a model. I'm just testing BCA. So I have X X, it's my images. I divided it by 255 to normalize it. So now all features, all pixel values are between 0 and 1. All pixel values are numbered between 0 and 1. And after that, I will use a PCA. I have PCA equal PCA number of components. It's a number of features which we want to get, in fact. And it's 8 times 8, it's 64, right? So I try to extract the 64 principal components, right? So here when you decide number of components, those number of components, it's number of principal components. I select 8 times 8. 8 times 8, which means it's 64. So do you see how much reduction from 784? And from those 784, I select 64 components, principal components. But just remember, in BCA, we have transformation. But if you use select k-best, there is no transformation. So I'm using it, I'm fitting it into this BCA my X, only X, because it's unsupervised. And I'm finding this cumulative sum of explainable variance. We should plot a graph here to show you how much explained, but maybe I forgot to do it here, in fact. So please try to plot this one. Try to plot this one. And after that, this is the reduced set transform. So I have the reduced set. So in fact, X here, it's 784 features, and X reduced, it's 64 features, correct? So it's really reduced a lot. It's like more than 90% reduction, in fact. 90%, it's compression, in fact. We compress the data. We try to transform it into another coordinate system, and try to compress it. So instead of representing each image by 784 values or number or pixels, I try to represent it by 64. You can also reconstruct it, in fact. You can use BCA inverse transform, and in this inverse transform, you will inverse transform X reduced into the original shape, right? If you want to. So I'm doing it, and finally we will get this one. Sorry, this one not 144. Sorry, this one is not correct. This one it's 64, which is more challenging, in fact, more challenging. So now this one, it's the original set. This one, it's the original set, and this one, it's the reconstructed set. It's reconstructed using 64 values. And when you look into it, it still has lots of information. This one was 5. This one is still 5. This one was 0, still 0. So we are able to read it, right? We're still able to read my images. So those images, it's reconstructed using 64. This one reconstructed. This is the original, in fact. This one, it's the original. If you want to make it more challenging, in fact, maybe you can just say, okay, I will reduce it to 32, and I will see if those images still have any meaning for us or not, using the principal components. So in fact, those principal components, they are very powerful. And you can see here, we can reconstruct the same image, and we are still able to read the digits using those 64 principal components. So principal components, it's very efficient. So it could be a task for you, for example, to use BCA with MNIST dataset and try to build a more simple model and check accuracy, what is the performance. I mean, the model will be more simple. The chances to overfit it will be much lower, and you will almost get the same results. You will almost get the same results using the original set. Maybe also it will be much better, because maybe using the original set, you need to have a more complex model, and when it's more complex, chances will be much higher to overfit. So I still also I have a mistake here, because this one it's not 144. This one it's 64 pixels. So I did SGD classifier for MNIST using this reduced set. So I divided the data here into a training set and a testing set because I need to test my model. I build a classifier and I trained my classifier using, wow. Okay. Because this classifier was trained using X train, Y train. Oh, sorry. So I have here X reduced, right? I reduced it using BCA before, using 64 sets. So I have now X reduced and Y reduced. In fact, this one should be Y reduced. No, sorry, Y should be the same. Y should be the same. So we have X reduced and Y. So this is my new data set after BCA. So this one, we got this one from BCA, correct? This one now, I mean, the size of this one, it will be 64 times this number, 60,000, for example, correct? So instead of working or 6,000 times 64, in fact, in reality, 60,000 times 64. So now we have this matrix. So instead of working with 784, we are working with 64, and we trained the model. So the model now will be more simple, correct? And we have the confusion matrix for the test set. And this is the accuracy, in fact, for the test set. Accuracy, precision, and recall. I mean, this one was a star. It's for a reduced model. This one was the star. It's a reduced model. And this one, it's for the original, the one which was trained for the original data set. So I mean, the accuracy has been reduced a little bit. So this one, it's 19.9%, but for the reduced set, it's 19.5. So there is no big difference, in fact. But you can just imagine how much data do we need, how much reduction in my features, training time, and so on. I mean, this example, it's just to show you the impact of using a principal component analysis. But imagine that if you are working with a data set which consists of thousands of features and millions of data points, so instead of training your model in 2 weeks, you can just train your model in 2 hours. It will be big improvement. So sometimes you can sacrifice the accuracy a little bit at the cost of, I mean, training your model in a shorter time, right? Because if I need to train my model in 2 weeks, for example, I mean, so what will happen if I need to modify it and tune model parameters and so on? It will take months to build your model. But if you can use BCA, for example, and try to simplify your data set and train a model much faster at the cost of, I mean, other many things, I guess it will be a big achievement. Yes, this home assignment, it's not for us, in fact. I mean, we still need to agree on the first home assignment. I want to make something more, maybe more simple. So it's, I just, if you have any proposal for your first home assignment, just please contact me, and maybe next week we can decide which home assignment should we work on. If it will be individual home assignment or if it will be one home assignment for all people. So please just let me know if you have any questions or in that part. And Magnus, if you are done with your part, you can just share your screen with me. So just we need to fix small things here in this code because I did some mistakes. I mean, those features, they were constructed using 64, not 144. So now we have Magnus.
Yes.
Yeah.
So I've well, everything is the same as before, except now I've separated out the actual drawing part of it, and being able to pick whichever image it is interesting shows that there is essentially no correlation between the reduced shape hair and the actual image.
Mm-hmm. So you used how many?
I used 12 by 12, well, 144, yeah.
Mm-hmm. There should be some correlation, but maybe I mean, the reduced set, it will be something different, but maybe
it might be not human obvious correlation.
Yes, it will be like barcode, for example. Do you know this barcode, and it's something coded, correct?
And isn't this the entire point? It's that it's not necessarily transparent to humans, but this is apparently reasonable to the machine.
But can you increase those 144, for example?
Yeah,
make
sure.
it 169, for example,
169.
because it will be 13s times 13s.
Yep.
You need to reshape it into.
Oh yeah, no, I've set that up to be automatic, so that's fine. It still doesn't really give you anything nice.
Can you try another image? It looks like 2, by the way.
Does it?
So the 2 there, you can kind of see the 2, and on the 5 you can kind of see something similar to the 5.
Yes, I can see it, by the way. 3 looks
Maybe.
It looks, yeah.
Maybe.
Oh.
It looks 30.
You have to really be on the side of the computer to give him this one.
Maybe if you can increase the, maybe you can go more, not 169, 14. What is 14 times 14?
14 is something.
You can just write 14 times 14.
Yeah, that would have worked.
Because when we are closer to the original one, maybe it will be just normal. Yes, it looks 0, by the way. It looks 0. Yes, it looks 9. It looks 9. Yes, it's 0.
Maybe.
Yeah. Do you know why? Because we are, I feel that in this example, we try to get the most important pixels, which are in the middle. But because we are, I mean, we plotting it in this dimension. If you can plot it in 28 times 28 with other cells or other.
Oh, yeah. And then size it down. That should probably help a bit. Yeah. How would you do that?
I don't know, but
I can think of a solution, but it's going to take some time.
Okay, no problem. But if you can share with me this piece of code, please, it would be nice. So I can add it to the slides.
Yeah, absolutely.
It would be nice. And thank you very much, Magnus, for your effort.
Yep.
So, so anyone has any question for today? Any questions for today, or? I mean, next week, the lecture for next week, it will be error backpropagation. We should start with it, in fact, but maybe now it's a good time for error backpropagation, because error backpropagation, it's complex algorithm, and it will take time in mathematics, maybe 20 minutes, for example, to explain it. And after that, we will try to implement it step by step. Maybe some of you can add L1 and L2 regularization, for example. Early stopping, for example, you can try to do it. Maybe drop out also. I didn't do all this. I just implemented error backpropagation, just minimizing a cost function, which was very simple. But if you want to add more extra work to it, you will be free to do it. So next time we will talk about error backpropagation, and we will apply also. We will build a model from scratch using error backpropagation. It will be feed-forward neural network. It will be like multi-layer perceptron, right? But it with one hidden layer, only one hidden layer. Because, but if we need to expand it to multiple hidden layers, we can do it. And we will apply it to iris, I guess. And we will see lots of curves and stuff like this. So it will help us, in fact, to understand the error backpropagation. How can we implement it? In error backpropagation, we go forward, and after that, we go backward to adjust weights. So it will help us to learn a lot, in fact. So it will be the task for next week. You did that already, Magnus. So I will share my code with, with you next time, or maybe this week I can put it in Blackboard, for example, and it's already in I can just show you the code, my code, so you can play with it, in fact, this week, and you can try to add L1 and L2. You can add also dropout. If you can add dropout, it will be fantastic. So just a minute, I will open my slides for next week. It's, in fact, it's in my computer all time. Lecture number 6, because I will just share it with you, and you can go to the link.
I might just put the code in a Python file in the chat. You might see.
Okay, my lecture.
Well, I think you sent it to me and not
I
to
did.
everyone.
Yeah. I did.
So I will share the code for. Okay, so this is the one which you sent.
Yeah, this is the stuff that I just showed.
Okay, I will save it to my computer here. Yes, thank you very much. I will open my slides. Okay, so strange. I cannot see my slides. Okay, do you see? I don't know if I'm sharing it with you, but I can share.
No, not yet.
Yes. Now you can see it, right?
Yes.
Okay, so this is for next week. I mean, next week, it's not long, in fact, because I mean, it's 15 slides, but maybe if we have time, we can do more funny stuff. But I hope if you can start, I will upload it to Blackboard today, for example. We will try to, I mean, I just started with gradient descent, for example, using some functions. I have some, we did that before, in fact, for simple functions like this one. So if we started from this point, if we started from, so for example, if we started from here, we will reach this point in that direction. If we started from here, we will reach this point. This one, it's a global minimum. This one, it's local minimum, which is not good solution. In fact, we need to reach this point, not this point. So this is the problem of gradient descent, in fact. This one, it's for a function which one-dimensional. I mean, I just upload this function against x, right? So this one, it's x, this one, it's f of x. I did it for function in 2D. So this, it's function of x1 and x2. We started from this point and we need to reach this point, and it works fine. And after that, we will go to back propagation. So we will see those equations. How can we get, we started by the error function, and we will get partial y by partial y by partial w. So where is it? So partial e by partial y. So finally, okay, maybe I'm missing something here, but so anyway, we will check it next week. And I have the code implementation. I implemented it by myself. And I assumed that we will be working for stochastic gradient descent. And in stochastic gradient descent, we update for each example. In fact, we update for each example. So so if you can go to this one and try to we need to try to do add dropout, for example. Can we implement a dropout? So in dropout, when we go forward, we will keep it, and then when we go backward, we will drop, for example, 50% of the nodes and the weights connected to those nodes, right? We will not update those weights. So it will be great. And if we can add L1 and L2 regularization techniques, it will be also very good. And after that, I used it for iris dataset, in fact. So I trained iris dataset using my model. My model, I called it feedforward, and we can specify the training rate, for example, learning rate, number of epochs, and also no, just number of epochs, and also number of units in the hidden layer. So I have only one hidden layer, and we can select this number of units in the hidden layer. I selected n equal 4, which means we have 4 nodes in the hidden layer. So we should do this next week. And for iris dataset, of course, we have 4 inputs. So we have x1, x2, x3, and x4. and the output, we have 3 classes. So I used one hot encoding. So it will be 1, 0, 0, for example, when it's a class 1. It will be 0, 1, 0 when it's a class 2. It will be 0, 0, 1 when it's class 3. And I can achieve accuracy, which is 90%. Of course, those 90%, we can increase those 90% if we can use L1 and L2 regularization techniques, for example, drop out, for example, and so on. So I will, you have this link, so you can get the code and you can play with it. You can try to modify it and make it more, more powerful. So we will do this next time. And I mean, the home assignment next time, it will be try to extend this error back propagation to multi-layer neural network. How can we extend this one to multi-layer neural network? Because I mean, the example which I solved here, I just assumed that we have only one hidden layer. So what we need to specify number of hidden layers. For example, I want to do 2 hidden layers. Someone else wants to make 3 hidden layers. So can you create this? Can you extend it to multi-layer? And can you add drop out? Can you add L1 and L2, for example? Early stopping also, it should be possible because we can watch the validation error here or validation accuracy, and we can we can predict when we will have this overfitting problem, and we can stop our training process, for example. So I mean, there are lots of things. If we need to work in one part of those, we can spend lots of time, but the slides for next week will be much less than this week, and we will see if we can do something more next week, or we can just work only with error back propagation. Yes, so thank you very much for today, and we will meet again next week. And please, if you have any questions, just send me an email or just call me. I will share links for recordings of today in Blackboard, and if you have any suggestion for the first home assignment, you can just send me email and we can discuss it. So thank you very much for today.